Hallo, hallo? Yes. It seems to clap.
Rein theoretisch müsste ich das bei dir unter Live jetzt finden, oder?
Ja. Excellent connection. Was sind da los? Irgendwie. Also da ist jedenfalls das Signal und so weiter, ne?
Oh, da kommt ein Schwarzer. Super. Muss ich da vorne was bewegen, damit er anfängt?
Das glaube ich nicht. Also es bewegt sich ja auch was, ne? Wenn die Leute bewegen sich, ne?
Ja, ich schon.
Das hilft das alles nichts,
Aber
weil
zeig mal auch dir nichts an. Das ist komisch.
ich muss jetzt pinkeln.
Solltest du lieber machen, ja.
Also nicht hier, aber. Tschüss. Was? Echt? Nein. Ein Blick und du nörgelst, ja? Ja. Hello. I think we have a nice tradition in this lecture to make the technical support somehow not work. So there's one version of the video where there is no video, but sound. Now there's a version of the video where you have video but no sound. Combining the two is not good. So Christian Angrich here improved everything so much that I think now the stream and the recording should work. Thank you very much, Christian. Of course, you made a mistake because now you will be blamed if it does not work. All right. Will you fall asleep if we do it like that? Likely. All right. Is of course that m gradient phi has to be evaluated at time t prime, and we saw that the little phi here, so the gravitational potential in this particular context, needs to satisfy the Poisson equation, the simple Poisson equation a phi times delta, where a phi is some function of time, and delta is the complete density contrast. All right, and then we saw that this Hamiltonian propagator, is nice and so on, very friendly, but it has one important disadvantage, namely that it's bounded from above, and so particles don't get very far. And this means that since this is a essentially very complicated integral equation, right, because we have to evaluate the force acting here along the trajectory that we want to have. A complicated integral equation. We want to solve it perturbatively. pH is too small, then this will be a large correction, and then we have no chance to really solve this perturbatively. So this is not good. All right, and then approximately at the end of the last lecture, I told you that we want to have something different for this reason. And what we rather want to have is plus or minus whatever something to figure out. Right? So we want the free trajectory, so the trajectory on which no force is acting, to satisfy this equation. How do we do that? I told you last time already that it's our choice what kind of reference trajectory we choose. And Newtonian axioms tell us that in Newtonian mechanics you take usually the inertial motion of a particle as the reference trajectory, and you call everything that deflects the particle from that the force. I told you that in general relativity the situation is different, because there we introduce the motion of free fall as reference trajectory. And then, of course, if you do that, like in general relativity, then there is no gravitational force anymore. But this illustrates that we have a choice what we want to use as a reference trajectory. All right, we'll see later how this works. But what I wanted to show you before is that there is an excellent reason for demanding a free motion that goes like that, plus some correction terms, and we'll see about this. But in order to show this, I want to make a brief detour to illustrate what is called the so-called the Seldowich approximation. Right? So suppose I start with trajectories like this, with a function of time that I call b now, because I want to show that choosing b equals t is a good choice to begin with. Right? But so I start with this ansatz here, and then remember this initial momentum here is different from the initial peculiar velocity only by the effective mass, which we set arbitrarily to unity initially. So initially, this is also the peculiar velocity here. And I'll switch later to that. But let's start with this. Now, by mass conservation, the density that I can expect at time t will be given by the density initially divided by the determinant of the Jacobian of this mapping here. Right? This just means that this flow here compresses or expands the matter. And since matter flows with these trajectories, matter does not move away or does not move out of a particular volume d3q that I'm looking at. So mass conservation demands this equation here. All right. If I start with motion like this, then the Jacobian is given by the unit matrix in 3 dimensions. That's this here. Now plus b times the derivative of that, the initial momentum, with respect to the initial position. But as we saw, right, the initial momentum is equal to the initial peculiar velocity, and the initial peculiar velocity we assume to be the gradient of a potential. So P is grad psi. So this would be the Hessian of the velocity potential here. Right, so the logic behind this is P of I equals U of I by our definition of the initial mass, of the effective mass. And this is the gradient of some velocity potential. And you saw in problem sheet number 2 that if you had a curl component to the velocity field, this would die out. And so this is not a bad choice. All right. This thing here, the Hessian of psi, is also called the Seldowich tensor. We'll see why. Okay. So what is the determinant of J? Well, in general, that's a complicated thing, but if this deviation from unity is small. There is an approximate equation for that, namely 1 plus b times the trace of d2 psi. Now you can either believe this or we can show it. Right? Proving this is not difficult at all. This is a symmetric real matrix. You can diagonalize it. Since the determinant is invariant under rotations, we can calculate the determinant after diagonalizing this. So if I diagonalize it first, the determinant just decomposes into 3 factors. 1 plus b times first eigenvalue times 1 plus b times second eigenvalue times 1 plus b times third eigenvalue. To lowest order in b times eigenvalue, this is just 1 plus b times the sum of the eigenvalues. The sum of the eigenvalues is the trace. Now this is valid in all frames. Right? Okay. But the trace of d2 psi is the Laplacian of psi. Right? I mean, the Hessian just consists of all the second partial derivatives of psi. If I take the trace, it's the Laplacian. But the Laplacian of psi by the continuity equation is minus the initial delta, the initial density contrast. Okay. I think we showed this before, right? I mean, remember we had delta dot equals minus divergence of the peculiar velocity field. So this is valid also at initial times. Now on the right-hand side you have minus nabla square psi. That's what I wanted. Here we have a delta dot. We know that initially the density contrast is evolving like the linear growth factor, but the linear growth factor is our time coordinate. So delta dot initially is delta dot initial. Okay, so if I evaluate this equation at the initial time, I have this and then I arrive here. All right. This is an approximation for early times. Okay, but let's insert it here. So then I can conclude that at early times, rho of t is just the initial density divided by this determinant. So I divide by 1 minus b times delta initial. But I'm linearizing anyway. So this is times 1 plus b times delta initial plus terms of second order in delta, or delta times b. All right. Now I can write the two densities on both sides by the density contrast. So this is 1 plus delta times the mean density. And since I'm working with co-moving coordinates, the mean density is staying the same all the time. Right? So this is approximately 1 plus delta initial times the mean density times 1 plus b times delta initial. Okay. Mean density drops out. So to first order in delta, this is 1 plus b times delta initial plus terms of higher order in delta. Okay? Now I can subtract the 1 on both sides and I get delta is approximately 1 plus b times delta I. This is the result from this equation here, with some arbitrary function b. But of course I must have, or I should make sure, that this is d plus times delta I, right? That it reflects at early times the linear growth of the density fluctuations, which goes with the linear growth factor, which is d plus. So you see that there is an optimal choice for this B. The optimal choice is such that this equation is satisfied, because then I know that this free motion here will already produce linear growth, linear density growth. Okay? Namely, if I choose B equals D plus minus 1, well, this is our time coordinate, right? So if I choose B in this way, B equals T, then free motion of the particles will already reproduce linear structure growth. So there's gravity without gravity, right? Linear structure growth is caused by gravity. Here we exclude gravity. Of course we don't. Of course we don't, right? Because our time coordinate already reflects linear structure growth. It's chosen such as to reflect linear structure growth, and linear structure growth you add already gravitational interaction. That's one thing. The other thing is that we are using this here, right? That density fluctuations are correlated with the velocities. So this means where I have an overdensity, I have a convergent flow, and this gives rise to structure formation, of course. So it appears as if we would neglect gravity here, but of course we don't, right? Simply by the choice of the time coordinate and by the choice of the velocity potential here, which is related to the initial density contrast, we do include gravity to some degree. We'll see more precisely to what degree. Nonetheless, this shows you that this choice here for the unperturbed trajectories is in this sense optimal. It's optimal in the sense that linear structure growth is already represented by a free flow of the particles. But now, of course, we have introduced a new reference motion. And we need to see how we need to correct the force then, such as to act relative to the new reference trajectories. And this can't be the original gravitational force, right? Because we know that the original gravitational force relative to the Hamiltonian trajectories here will reproduce structure growth. Now we have chosen trajectories which, without any additional gravitational interaction, reproduces linear structure growth already. So we have to correct the Poisson equation in some way. Let's see how. But this is called the Seldowich approximation. I mentioned this last time already briefly. And Seldowich came up with this in a famous paper in 1970. Later, we will have to have a closer look at this object here, the Seldowich tensor, because as you will see, the eigenvalues of this tensor have very interesting properties. But we'll see about this later. Okay. Suppose you buy this, right? Suppose you buy this. Then we need to see how we now have to correct the force acting relative to these Seldowich trajectories. All right. In order to do that, I just start with the first equation there. And then I rewrite this in a way as I would like to see it. And then we see what we do. Okay, so this is not the first trajectory. In order to get the first trajectory, I need to write this, right? Now, obviously, we have the the previous trajectory back, right? Because I write what I would like to see, I subtract what I would like to see, then I need to correct with a Hamiltonian propagator. Okay. Now I'm going to manipulate this equation. It's a Seldovich trajectory. And now I'm going to pull this expression here under the integral. How can I do that? Well, I need to take the time derivative of this. So the derivative of this expression here with respect to time t, I need to distinguish between times t prime and t. Right? So I need to specify this. And then I'm going to switch sign, right? So I can pull this under this integral with a minus sign. So I'm writing minus integral from 0 to t dt prime of what? Well, 1 minus gh dot of t and 0. Now I need to integrate over this. So this now needs to be t prime, right? Needs to be the integration variable. And the dot refers to the first argument of the function gh. Right? The function gh has two time arguments. So I need to say which time the dot is going to act on. It's the first time argument. Important. Okay, now this is going to turn into this because the initial momentum is an initial momentum, as the name is telling, and so it is independent of time, so I can pull it into the integral. Lovely. Okay. The rest just remains. What was GH again? GH was this. It's the integral over the inverse effective mass. So what is GH dot? I told you the dot acts on the first argument. So GH dot for any second argument is the derivative of an integral function with respect to its upper limit. So it's just the integrand evaluated at the upper limit. So it's 1 over m of t. Or rather, it's 1 over the mass taken at the first time argument. So this is q plus t p minus integral 0 to t dt prime 1 minus 1 over m. One moment. 1 minus 1 over m, but now m of t prime, right? Times p minus gh t and t prime m gradient phi. All right, now your question. There's a plus, yes, you're right. Because I pulled the minus sign out front, yeah. That's true. Okay, now we are here. Doesn't look good. So let's apply some cosmetics so it looks nicer. now I want this expression here to look like this. I demand there exists a function AP of t prime such that I can write this expression here also with a Hamiltonian propagator. Let's see whether that exists. I take a first derivative with respect to t. So here the only appearance of t is in the upper limit of this integral. So this, on the left-hand side, this derivative with respect to t just gives me the integrand at t. So this is 1 minus 1 over m of t now. On the right-hand side, I need to be careful, right? There are two appearances of t, so I need to apply the product rule. If I take the derivative of t with respect to the upper limit here, I need to evaluate the integrand at the upper limit. This would mean I have to replace t prime with t here, so I get the Hamiltonian propagator from t to t, which is 0. Done. So what is left is the integral 0 to t dt prime of t h dot. It's a dot. Okay, and th dot is 1 over m. So this is integral dt prime 0 to t ap of t prime divided by, look with that, this derivative of th dot is taken with respect to its first argument. First argument is t, so this is m of t, not m of t prime. So in terms of this t prime integration, this is a constant. Okay, so I can multiply this equation with m. So I get m of t minus 1 equals integral 0 to t ap of t prime dt prime. Now I take another time derivative, because that's really funny. So I get m dot of t equals ap of t. So I know what AP is. It's m dot. But we also know what m dot is, right? Remember, we calculated this already. And we found that m dot is m a phi d plus. I'm alluding to a result we had earlier, right? We calculated m dot. We found it's m dot a phi d plus. And with that, I'm returning to our previous expression. So I can write this as q of I plus tp, not of I, qi plus tpi. So low trajectory, now minus integral 0 to t dt prime. Instead of this whole expression, I can now write, first of all, th of tt prime. This is how we close AP. This is now a factor common to both. Then I have AP, but m has a factor of m, sorry, AP has a factor of m in it as the next term. That's an m of t prime. All right, what is left now is, let me write this first, it's the gradient of phi as we had it before. And we have an a phi d plus times the initial momentum. But the initial momentum is the initial peculiar velocity, it's the gradient of psi. And you see that suggests introducing yet another potential. Well, I'm gradually running out of phi's. So I need to recycle phi's I used before. How about this? Let's define it as phi plus a phi d plus psi. Okay? Then I can write the whole expression as gradient this other phi, and have the new potential acting relative to our Seldovich trajectories by means of this Hamiltonian propagator here. Now let's have a look at the Poisson equation of this thing. That's particularly funny. Blackboard recycling. Let's take Laplacian of phi. That's the Laplacian of small phi, and the Laplacian of small phi is a phi times delta. Now we have a common factor of a phi. Laplacian of psi is minus delta initial. But what is this? That's the density contrast minus the linear density contrast. So what remains as the source of this potential phi is only the nonlinear density contrast. In other words, the density contrast you get once you subtract from it the linear density contrast. Okay? So this is a phi times the nonlinear density contrast only. And this is why the Seldovich approximation is so damn good. As long as the evolution is linear, there is no gravitational force relative to the Seldovich trajectories. Only as nonlinear structures are building up, there is going to be a force relative to these Seldovich trajectories. So as long as everything remains linear, you have free streaming. And that's easy to calculate. All right. That's what I wanted to show you. This is the main reason for introducing Seldovich trajectories here. Because you see that now, since the potential is sourced only by the nonlinear density contrast, we have a good chance of getting through with a perturbative ansatz, right, with an iterative solution to our equation of motion. Because initially there's just no gravitational force. So initially, the right-hand side of this integral here or rather integral there is 0. And then we can iterate ourselves away from that. Okay. Summary. Summary. We can write our trajectories in configuration space in the very simple way Q initial plus T times P initial. And now let me do the following thing. I will now specifically replace the pi here by ui to make clear that we are now dealing with velocities here rather than momenta. It will become more clear soon. Minus integral dt prime 0 to t gh of t and t prime m times gradient phi, where phi satisfies the Poisson equation sourced by the nonlinear density contrast only. These are the most beautiful trajectories we can use, right? And they are beautiful because linear gravity is contained in the free streaming. The additional gravity is sourced by nonlinear density contrast only. This means, by the way, that the gravitational force relative to these trajectories has no longer infinite reach. Right? The Newtonian potential just goes like 1 over r, so it extends to infinity. Relative to these trajectories, that potential does not. Right? We are speculating about this potential here having a Yukawa form. We don't know this yet. But in any case, there will be a large-scale cutoff to this gravitational potential phi because of this Poisson equation here. Right? So it is not generally true that gravity is represented by a potential with infinite reach. Depends on the reference trajectory you choose. This is no miracle. Think of general relativity again. There you introduce the free fall as reference motion. And relative to the free fall as reference motion, there is just no gravitational force. Not even a short-ranged one. So this is not particularly miraculous or so. It's just a more appropriate choice of reference trajectory. And relative to those trajectories, gravity becomes, Newtonian gravity becomes short-ranged. Now this should electrify people who are running numerical simulations, right? Because if you have short-range gravity, you don't have to sum over all particles in your simulation box, but only over those nearby. So far it didn't catch. Okay. Yes?
So this is like in general, it's not in linear theory, but in general.
That's general, yes.
So why, when we derive our reference frame, why we choose this propagator to be t minus t prime? We actually impose that the density contrast was the linear density contrast at some point.
No. When we
show that this b we started with was
okay. I just showed that if you put an arbitrary function of time here, then it turns out that linear growth is reflected if you choose, or is already represented by free motion, if you choose b equals t. So this means that you construct the prefactor of the initial peculiar velocity such that this already contains linear structure growth. And the rest is taking care of the nonlinear structure growth. All right. Now, sometimes it would be nice to write this. Why is this nice? Because then you would have the same propagator under the fourth term, t minus t prime, and outside the integral. That makes formulating the propagator in this equation as easy as possible. But of course, then you will have to determine a new force. So how do we do that? just to make it clear, I'm writing the force now as a function of t prime to get this complete. So we need to determine the force, such that it represents the rest, right? And I'm doing this with a minus sign, so that the negative potential gradient is the force. Okay, so it's this fine. Okay, so I can achieve what I wanted to have if the left-hand side is set equal, or can be set equal to the right-hand side. So, yeah, same as before, right? You take a time derivative. If I take a time derivative again, I have to take into account that here is a time and here is a time. But if I just evaluate the integrand at the upper integral limit, it's getting 0. So the only thing that contributes is integral 0 to t, the time derivative with respect to t of this expression. So this is just f of t prime. So this already shows that the next time derivative will take us where we want it. But this needs to be equal to, if I evaluate the integrand at the upper integral limit, it's getting 0. So the only thing I have to take is 0 to t dt prime, time derivative of the Hamiltonian propagator, that's 1 over m of t. Time derivative of this doesn't matter because it doesn't depend on t, but on t prime. So to be sure, I have to distinguish an m of t prime from an m of t here. And the gradient of phi, well, this has to be evaluated at time t prime as well. All right. Now take another time derivative. Let's give it an arrow. Deserves one. So by another time derivative, we get the fourth term now. So now I have an m of t that I can pull out of the integral, but of course does also depend on t. And I do get now a contribution from taking the integrand at the upper integral limit, because then I just get m of t prime evaluated as c prime equals t divided by m of t gives you 1. So you get gradient phi, of course, but now you get a correction term which comes from taking the time derivative of this thing. So this is minus m dot over m square taken at time t. Now times the integral over m of t prime gradient phi dt prime 0 to t. Okay, now of course you could replace m dot by m a phi d plus if you wanted, but let me stop here. Now we have an expression for the force if we insist on using the same propagator inside and outside the integral. So I can write the same trajectory in this manner here if I'm willing to accept this more complicated force term here. All right. And then you can see that if you define the phase-space trajectory as q and q dot, not as q and p, but as q and q dot, then you can write this phase-space trajectory simply as g of t and 0 times x initial plus integral 0 to t dt prime g of t and t prime times f of t prime And G is now a Green's function or a propagator that is as simple as possible. Namely, it's just 1 t minus t prime 1, 0. And the ones mean unit matrices. Okay. So now we have a choice, right? We can either if we insist on having a simple force term, use this representation of the phase-space trajectories. And this is advantageous for some cases, but it immediately shows you that what causes the deviation from the Seldovich trajectories is the nonlinear density contrast and not the complete density contrast. And this is a decisive advantage. This form of the trajectories here is particularly nice if you want to have a simple expression, but then you have to deal with a more complicated force term. Like this. Okay? The main messages are, number one, we are free to choose a reference motion as we like. Number two, the Seldovich reference motion is preferred. Number three, relative to the Seldovich motion, a force acts which is sourced only by the nonlinear density contrast, and which is therefore ideal to solve this integral equation here, iteratively or perturbatively. And you can bring the same trajectories into this form here with a very simple propagator G here. Done with the trajectories. Are there questions? Isn't this lovely? All right. Now we need to do some statistics. And of course, in an analytic calculation, we do not want to repeat a numerical simulation. Because if you want to have a nice picture of cosmic structures, you should rather run a numerical simulation. So what we can do here is not evaluate particular ensembles of trajectories forward in time, but what we can evaluate is statistical properties of densities, trajectories, and so on, described in this manner. So we need to talk about statistics of cosmological fields. And now we have to make a detour through statistical terms that we will use a lot as the lecture proceeds. And the main terms are, of course, Gaussian random field. Then we need correlation functions and we need power spectra. And of course we need to introduce what these are. And I wanted to explain why Gaussian random fields are so frequent. And wherever you meet somebody who needs a random field, people will choose a Gaussian random field. Why? There are good reasons for doing so. The reason is the central limit theorem, and since the proof doesn't cost very much, except your patience, I will prove the central limit theorem. And thereby show that Gaussian random fields are not something that you choose because you don't know how to do better, but there are good reasons for doing that. Right? Okay, but we'll see. Okay, so statistics. And if you have a look at the lecture notes that are growing on the web page of the lecture, this is chapter 3 of these lecture notes, and there you will find at least what I'm going to cover today. All right, the central term we are starting from is a random field. What is a field? A field assigns a value to any point in time, to any point in space at any given time. Electric field, magnetic field, you know that. What is a random field? Well, a random field assigns a random value to any point in space at any given time. Random fields could, for example, be the density contrast in the universe. There's a certain stochastic process behind populating a random field with values. This could be a Gaussian process, then we have a Gaussian random field, and so on. But we'll see about this. So that's a random field. And suppose I call the values of this random field x. This is not a position in space now, right? This is a value assigned to some position q in space at some time t. So x can be a d-dimensional vector, like, for example, with a peculiar velocity field. So then x would be a three-dimensional vector. X could be a one-dimensional thing, right, a number, like for the density contrast. X could be a 4 by 4 tensor if you have a random background of gravitational waves, for example. Okay, so it's a thing with d dimensions, and we assume that we have a probability distribution from which we can draw the values of x, so that if I choose a field value to assign at any point at any given time, I can draw it from this probability distribution. All right. Now we need some terms, and the first term I'm going to introduce is the so-called characteristic function. Phi of t, which is the Fourier transform of the probability distribution. It's the Fourier transform for probability distribution. Now, since x is a d-dimensional vector, t also has to be a t-dimensional vector. And for now, it just has the meaning of a Fourier conjugate to whatever x is. Now, okay, let me introduce some notation also. This will be an integral over x. And I'm using this as a shorthand notation in the following way. X means an integral over the complete vector x over the d-dimensional domain that we choose. This would usually be the Rd, for example, but could be another domain as well. Also, I'm introducing a notation for Fourier variables, Fourier conjugate variables, because we will spend a lot of time in Fourier space. And there I'm going to put the complete 2 pi vector, the complete normalizing, sorry, not vector, the complete normalizing 2 pi factors into the k integral and nothing into the x integral. This I abbreviate as, integral k. And then I use as a Fourier convention that the Fourier transform of a function f evaluated at wave vector k is given by this convention here, and that the inverse Fourier transform of a Fourier transformed function f tilde, if there result evaluated at x. This is the integral over k, f tilde of k, e to the I, k times x. That's just fixing the Fourier convention. All right. So these notations give this integral a meaning here. Now, since integrals over the probability distribution are averages, you often find this expressed as the average of the Fourier phase. It's not very intuitive, but it's correct. All right. Now suppose you take this operation I times dt to the power of k applied to the generating or to the characteristic function, and then you set t to 0. Then what do? For any derivative with respect to t, you pull x down, and you multiply the minus I factor by a plus I factor, so you multiply the sign and the i's away. So this is called the kth moment of the probability distribution. Now, if you set k to 0, then you evaluate just the characteristic function at t equals 0. This will just be the integral over p of x, that's 1. Right, so mu 0 is 1. If you do this once, you pull a factor of x down, you get the average of x. If you do this twice, you get the second moment of x, and so on and so forth. Now, of course, as it's written here, it's not very well defined if t is a vector. What I want to understand then is that this is the vector, the kth vector product. Ignore this for the moment, okay? Just to say that I didn't just overlook this point, but there's a meaning behind this. We'll clarify this later when we talk about, for example, power spectra of velocities and so on. Then we need things like that. All right. So this is why phi of t is also called the characteristic function. It's also called the moment generating function, because by applying this operation, you get the moments. Right? So normalization, mean, standard deviation, and so on and so forth. Now suppose you do this. You take the same operation, but now you apply to ln phi of t. Divide by t. Sorry, then you divide by phi of t upon the first derivative and so on. These things are called cumulants. The cumulants have nice properties, and we are going to need them. The nice properties are that if you apply the cumulant with respect to the sum of two independent variables, so we have an independent variable x1 here, an independent variable x2, then the cumulant is additive. Not going to show this, but this is quite straightforward. If the variables x1 and x2 are independent, and the cumulants are homogeneous functions, so if you insert cx instead of x up here in the definition, then they are homogeneous of degree k, right? And I'm just mentioning this because we are going to use these properties of the cumulants when we will speak about the central limit theorem, and afterwards you can forget them again. But they are really useful in this context, and then the proof of the central limit theorem is going to be really, really short. Of course, this is just pushing the proof into these properties here, which are more difficult to prove, but nonetheless. So you have these properties of the cumulants, additivity and homogeneity. And because ln phi is related to the cumulants in this way, ln phi is called the cumulant generating function. Okay. Now let's come to a Gaussian process. And as the central limit theorem will tell you, there are good reasons for thinking of a Gaussian process. But let's first define it and then see about it. Okay, so these are just general terms that we are going to use. Now, Gaussian RF, Gaussian random fields. For these, the probability distribution is given by a d-dimensional Gaussian, d-dimensional multivariate Gaussian. So it has a normalization factor. It looks like this. And then you have an exponential of this form here. All right. So instead of a simple square of x divided by sigma square, you have a quadratic form, x transpose times a matrix c to the minus 1 times x. And of course, for this to be meaningful, the quadratic form has to be positive definite. So c to the minus 1 needs to be a positive definite matrix. So this means that c, and therefore also c to the minus 1, can only have positive eigenvalues. Okay, fine. Now, well, this is just normalization, as I said. Since x is a d-dimensional vector, c to the minus 1, and therefore also c is a d by d dimensional matrix. Sorry. All right. So c is d by d dimensional, and of course we need to be able to calculate the inverse. So the determinant has to be non-zero. But of course we know that already because this quadratic form is defined to be positive definite. Okay, now let's calculate the characteristic function of this. In other words, let's calculate the Fourier transform of this Gaussian. And probably you know that the Fourier transform of a Gaussian is a Gaussian. But let's see which one. All right, so we want to calculate let me write the determinant now just with the absolute bars. We want to calculate what this thing is. And since this involves a trick that is used very often, let me show how we do this. Of course, the problem is, first of all, that this covariance, this x prime. Okay, and lambda is going to be a diagonal matrix of d positive eigenvalues. But now you see, now the argument of the exponential decays into some terms that only, well, where each of which only depends on one specific component of x prime only. So this is now a product of exponential integrals where the integration only extends over one of these components. Now we have xi prime squared divided by lambda I. Divided because we need the inverse of the diagonalized matrix here, and this phase factor here. All right, now this is easily calculated. It's a matter of patience, isn't it? And of persistence. All right. So now we calculate one of these factors and then we see about this. For one of these factors, I'm going to write let me write it this way. Some factor a times x squared minus I xy. Okay? Right now we integrate from minus infinity to plus infinity. And of course we do this as usual by quadratic extension. And we extend the argument of the exponential quadratically. So that's minus a half. Now root a times x plus I y divided by root a. Now if you take the first term squared, you reproduce this. If you take the mixed term, you reproduce that. but then we get the last term squared, which we need to subtract. But the last term squared gives a minus y squared divided by a times minus a half. So this gives plus a half times this. I need to subtract this, so I need to take minus a half y squared divided by a. Okay. The exponential of this doesn't depend on x anymore. I pull this out of the integral. Then I can transform the variable here by calling the complete argument of the exponential some new variable and integrate over this new variable, but then I have to divide by a square root of a. And the Gaussian integral is just giving me a square root of 2 pi. You know that, right? So this is e to the minus y squared divided by 2a times square root of 2 pi over a. What am I doing? Yeah, it's okay. It's the right thing, of course. Good. Now, let's return to our calculation of the characteristic function now. I'm using this result that I get for each of the factors. And I'm going, yeah. Where are you? Of course. Thank you. Good. So the characteristic function. Now look, we have a square root of 2 pi to the power of d, but I get this square root of 2 pi factor d times. So the 2 pi is gone. All the 2 pi factors are gone. Then I get the square root of 1 over a, which means the square root of lambda I for each of the factors. So I get a product of these square roots of lambda I. But the product of all the lambda i's is the determinant of c. So the determinant is also gone. How nicely this has been normalized, right? Okay, so all the prefactors are gone anyway. And what remains is e to the minus y squared. Now with the y squared, we need to be a bit more careful, because the y now represents the tx. No, sorry, the t for all the factors, but they are multiplied by 1 over a. And 1 over a's are just the lambdas, right? So I get, in the argument of this exponential here, a sum over lambda I ti prime squared. This is in the principal axis frame of the original covariance matrix. Now I rotate back. Then I get, this is t transpose times c times t. Right? Because this expression is t transpose times lambda times t in the principal axis frame. And if I rotate this back, then I get the rotated back lambda matrix, this is c, and I get the back rotated t primes, which are t's. All right, so the upshot is it's minus a half t transposed c times t. Aha. The Fourier transform of a Gaussian is a Gaussian. Almost, it's a non-normalized Gaussian. But look, the cumulant generating function is the logarithm of that. So it's simply the quadratic form times minus a half. If I take any derivative with respect to t, and then set the t to 0, the largest derivative I can get to is 2. And the first derivative will leave a factor of t, but we set t to 0. So the first cumulant will be 0. The second will be the largest I get. What's the 0th? Well, the log is 0 then. No, wait a moment. Yeah, the log is 0, and therefore the 0th cumulant is just 1. So there are two uninteresting cumulants, namely number 0 and number 1, and the only one of relevance is number 2, and it's also the highest we get. And this characterizes the Gaussian distribution, right? You have cumulants up to order 2 and no more than that. We'll need this. All right? Good. So I wanted to show you two things here. First of all, how do you calculate integrals like that? You transform to the principal axis frame of the matrix C, and then you go back. All right. Why do we get a first cumulant of 0 here? This is because of simplifications that I started out from. If you write x here, the average value of x is 0. Right? Because then the exponential function is symmetric with respect to x. If you evaluate the average, you multiply this by x and integrate over it, and it will be 0. I've chosen it to be like that, right? If you want to have a finite mean value, you subtract the mean value for both of these vectors x here. And if you start out from a Gaussian that contains a finite mean value, then you will get a first cumulant that will not be 0. But, of course, for any random field whose average you know, you can subtract the mean and start with what we call a centered Gaussian random field right away. For example, for the density contrast, we know right away that the mean density contrast is 0, and then the density contrast will be a centered Gaussian random field, and so on. Right? So since you can always arrange a Gaussian random field to be centered, I started with a centered random field right away, and then the first cumulant is 0. So what do we have? K0 is 0, K1 is 0, K2? K2 is what? You derive by t twice. Therefore, you get rid of the minus a half. You multiply, definition is gone. You multiply by the imaginary unit twice, so the minus sign is gone. So the second cumulant is just the matrix C. And then you see why I wrote that I want to have this expression interpreted as a tensor product here. But okay, turns out like that here. Okay. Now we have the characteristic function, we have the cumulants. Now we can proceed immediately to the central limit theorem and show why Gaussian random fields are so unbelievably frequent. And not just in the theorist's imagination, but in reality. So suppose you throw dice. Right? You have nothing better to do, you throw dice, whether it's bad or nothing useful on Netflix or whatever. And you throw dice, let's say, over the evening 2,000 times. Right? Sorry for your evening, but that's okay. And now you group these throws of dice into tuples of 10 each. Right? You throw your dice 10 times, and you repeat this 100 times. Right? Okay. So you sum over 10 throws of your dice. Sum all these values here from 1 to 6 if you have a decent dice. You divide by the square root of n, and you call this y. In other words, from your random numbers that you have generated, you create a new random number. And you just superpose old random numbers. Now, what distribution does y have? And you know what distribution the x's have. It's just a flat distribution. Well, depending on your dice, obviously, the expectation is that this is flat. Okay. Now we just use the additivity and the homogeneity of the cumulants. So I want to know what is kappa k of y. I use the homogeneity first. And get a factor of root n to the power of k. I use the additivity now. Then I get kappa k of xi. Whatever these are, right? I've only used homogeneity and additivity of the cumulants. Now I'm assuming, and this is what I have to assume about the distribution of which the x's are being drawn, that these cumulants are finite. And I particularly want to look at kappa 1 of xi, of which I demand that all of them are less than a, some finite number a, less or equal a. And the same I want for b. So I want for the second cumulant. Okay. Then I know that the cumulant kappa 1 of y is less than 1 over n to the power of k divided by 2. And now the sum will be less than n times a. So this is going to be n to the power of 2 minus k divided by 2 times a. But k is 1. So this is root n times a. In other words, the mean value of the distribution of y, this is going to grow. Right? Just because you're adding very many, but of course you can always subtract the mean value here. Now let's have a look at the second moment. This is less or equal. Let me just copy that, even though I could set k to 2 right away. This is now going to be n times b. Now, again, 2 minus k divided by 2. 2 minus k is 0, so this is going to be b. The second moment is finite. Higher order moments with k larger than 2 are going to be suppressed by this factor if n is getting large. Right? So if all the cumulants of the parent distribution are finite, and I just add sufficiently many of these random numbers, then the third and fourth and fifth and so on cumulant are going to be suppressed. In other words, in the limit n to infinity, if I subtract the mean, one of them will remain, it's K2, it's kappa 2. So this means the result will be a Gaussian. Okay? So whatever distribution you draw your original random numbers from, if that parent distribution has finite cumulants, which means that it has finite mean and variance, then the superposition of these random numbers will approach a Gaussian distribution. Very, very, very important. Try this out with dice, right? You don't need to do this yourself. Ask your computer. He's going to love it. Or she, depending on. Right? Try it out. Try it out. Sum 10 throws of dice and calculate the distribution of this number here. 1 over root 10 times the sum over these numbers. It will be a beautiful Gaussian. Start with a distribution like that, right? Just to make things awkward, right? Start with what could be a reflected Gaussian, and you do this with n equals 10, and you get a beautiful Gaussian distribution. It's amazing how this works, with very few numbers already. Try it out, right? It's really amazing to see. So, this is why we have very good reasons to think that, for example, the density contrast field in the early universe is a Gaussian random field. Because we believe that structures in the universe originated, for example, from a superposition of very many independent modes of a scalar field, the so-called inflaton field. You superpose many of them, they are all independent, you get a Gaussian random field, and so on and so forth. Right? So this is what comes out of this is called the central limit theorem. And the central limit theorem is the main reason for assuming Gaussian, for knowing that there are Gaussian random fields everywhere. Right? Wherever you superpose random fields to create new random fields, you will get a Gaussian random field. And this is why we are going to focus on Gaussian random fields all the way along. Right? Okay. I think we should stop here. Central limit theorem is a good point to stop. So what I wanted to tell you today are two things. First of all, how can we introduce reference trajectories which are particularly useful in our context? And we introduce Seldovich reference trajectories for good reasons, because they reflect linear structure growth already without taking any further interaction into account. But then relative to the Seldovich trajectories, the gravitational potential becomes sourced by the nonlinear density contrast only. And this is why, in this context, the gravitational force will become short-ranged. Number one. The rest was cosmetics, right? We played around with different propagators and so on, but this is the main message. Next one is we introduce the term of a Gaussian random field and use the concept of a cumulant generating function to show the central limit theorem. And on the way, we showed that the characteristic function of a Gaussian is a Gaussian, and so on and so forth. This was techniques, right? But the main message is there are good reasons to start from Gaussian random fields in cosmology. Well, and that's where we will continue next time. If there are no questions, then this is all for today. Thank you. Was?
Ich glaube, die Frage ist jetzt später.
Okay. Ja? Auf der Webseite der Vorlesung. Die ist,
Gar nichts. Ah, aber selbst auf dem Computer habe ich sie nicht gesehen.
Also ich hab's,
schalt mal auf Englisch um.
ja, oder auch noch eine Sprache. Also
Und dann
es war,
Ist ja der Hammer.
weiter runter, weiter runter.
Ja, ja.
ja, es war.
Da, da, da.
Okay.
Ich habe auch ein paar
Nee, ist nicht komisch, es liegt an mir. Du musst am Anfang, wenn du die Vorlesung mit ihren Parametern erzeugst und so weiter im Übungsgruppensystem, sagen, ob du es ein- oder zweisprachig haben willst. Und da habe ich einsprachig angegeben.
Deswegen,
Haha.
Tatsächlich noch eine Frage.
Ja.
Android ist also auch per E-Mail schreiben, aber
Gut.
Bei dem hier. Warum geht dieser Zusammenhang im Kontext von dieser Gleichung?
Weil ich lineares Wachstum voraussetze. Das heißt, ich führe Stromlinien ein. Also, du könntest auch allgemeiner anfangen, ne? Und sagen, du hast einfach Trajektorien Q von T. Die beginnen bei QI. Das heißt, wenn du dir 8 Punkte QI auswählst, dann kriegst du einen kleinen Würfel, transportierst ihn vorwärts. Nachdem die Eckpunkte dem Fluss folgen, wird kein Material den Würfel verlassen oder reinkommen. Also ist das Volumen dieses kleinen Würfels mal Dichte konstant während des Flusses. Ne?
Verschiebt letztendlich von den Würfeln. Nicht, verändert man nicht die Form von dem Würfel selbst.
Wir verändern die Form von den Würfeln. Also das Q von T ändert sich ja. Ne? Aber das Volumen des Würfels ist halt gegeben durch die Determinante dieser Transformation. Stell dir ein infinitesimal kleines Volumen vor. Es wird weiter transportiert durch den Fluss. Das Volumen ist gegeben durch die Determinante der Transformation.
Warum gilt es ganz lokal?
Weil die Ecken dieses Volumens, des infinitesimalen Volumens, das du dir raussuchst, mit dem Fluss mitschwimmen. Und die Ecken sind ja sozusagen markiert durch Teilchen, die selber wieder dem Hamiltonischen Fluss folgen.
Okay, das heißt, es folgt letzten Endes aus der Eigenschaft vom Fluss.
Genau.
Von dem Linear
Genau.
ist, dass es gilt.
Genau. Und wenn du nicht annehmen willst, dass sie das linear sind, dann nimmst du allgemeine Trajektorien Q von T, aber dann kannst du über die Determinante nichts mehr aussagen. Wenn du die lineare Näherung machst, dann ist die Betrachtung halt nur noch in linearer Näherung gültig. Ne? Aber solange es linear bleibt, zeigt es halt, wo heißt denn, diese Funktion B von T, die ist halt bevorzugt, ne? Weil sie das lineare Wachstum reproduziert.
Vielen Dank. Das war wirklich, ich habe mir das heute Morgen angeschaut und jetzt hast du es wieder bei dir gemacht.
Wunderbar.
Sehr gut.
Das war extra für dich. Die nächsten bitte.
Frage zum Übungszettel, und zwar bei der, wo man den Hamiltonian am Ende liest,
Ja.
hatten wir in der Übungsgruppe gestern als Anfangsbedingungen dann B0 und minus R für QI und hier 0, 0 V. Und ich habe jetzt nicht verstanden, warum hier dieses minus R noch dabei sein muss. Also das B ist mir klar, weil wenn man die Geschwindigkeit in die gleiche Richtung wählen würde, dann würde man hier nochmal durch das Potential, wo halt durch die Null durchgehen und da wird das Potential divergieren. Aber
Das ist keine gute Idee, wenn Sie eine erste Näherung machen wollen.
ja, eben. Aber
Also die Idee war, B muss genügend groß sein, sodass die Ablenkung schwach ist.
ja, dass man
Aber
halt hier
genau.
vorbeigeht.
Ja.
Aber würde es nicht ausreichen, wenn man hier dieses minus R weglässt und einfach nur hier B hat und von da dann...
Und von 0 anfängt, kriegen Sie halt die halbe Ablenkung. Ne? Also die Idee war, Sie kommen aus minus unendlich und Sie fliegen nach plus unendlich. Und um den Übergang sozusagen explizit zu machen, dachte ich, okay, fangen Sie mal bei minus R an, laufen bis plus R und schicken dann R gegen unendlich. Ne? So geht es auch natürlich, ne? Aber dann fliegen Sie halt sozusagen schon vom nächsten Punkt relativ zur Masse los und kriegen deswegen nur die halbe Trajektorie. Das geht auch.
Okay, dann macht das Sinn.
Na klar. Nur was?
Okay, danke. Ich habe eine Frage. Du hast ja gesagt, dass das Potenzial Short Range wird.
Ja.
Wie lange die Nicht-Linearität beschränkt. Und kannst du mir erklären, wie ich mir das vorstellen kann? Weil ich bin irgendwie nicht sicher, wie ich sowas aus der Poisson-Rechnung sehen kann.
Auf großen Skalen bleibt es bei linearem Wachstum. Weil da das sind die Dichteschwankungen klein. Und werden wir dann später sehen, ne, wenn Beobachtungen zeigen, dass es klein ist, dass die Dichteschwankungen auf großen Skalen klein sind. Und das heißt, auf großen Skalen bleibt alles linear. Und du kriegst das nicht-lineare Wachstum nur auf kleinen Skalen. Mit anderen Worten, die Gravitation sorgt dafür, dass sich zunächst mal kleine Strukturen bilden. Und dann breitet sich dieses Strukturwachstum zu immer größeren Skalen hin aus. Aber die Nichtlinearität wird bei den kleinen Skalen zuerst einsetzen. Und zuerst mal wirst du kleine Klumpen bilden und dann größere und so weiter. Und das heißt, dass der nichtlineare Dichtekontrast zunächst mal auf allen Skalen überhaupt nicht existiert. Und dann, wenn er anfängt zu existieren, auf den kleinen Skalen zuerst entsteht. Und das heißt, das Potenzial hat nur kleinskalige Fluktuationen am Anfang. Und das heißt, die Gravitationskraft ist auf kleine Skalen begrenzt.
Okay. Kannst du vielleicht irgendwas empfehlen, soll ich mir anschauen, meine Poisson-Gleichung wird? Weil ich bin auch nicht immer so gut. Weil ich bin mir ein bisschen unsicher nach, wie ich sowas aussieht.
Also, ich fange mit dem einfachsten Fall an. Du hast ja irgendeine Quelle. So, jetzt, wenn die Quelle kugelsymmetrisch ist, das kann die Quelle sein, die vom Radius abhängt. Ne? Wenn die Quelle kugelsymmetrisch ist, dann kann ich den Laplace-Operator hier in Kugelkoordinaten schreiben. Dann sieht das so aus. So, ja, Vorsicht.
Okay, das sieht schön aus.
Jetzt musst du integrieren hier drüber. Und du weißt a priori nicht von wo aus.
War das, was du gesagt hast mit diesen Grenzbedingungen, dass die bei den ausgewählten Flächen sagen?
Das heißt, du musst jetzt irgendwie auf Randbedingungen festlegen. Ne? Jetzt, also, das ist ja jetzt ein Gradient an des Gravitationspotenzials, eine Gravitationskraft. Da könnte ich zum Beispiel eine Randbedingung so wählen, dass das Integral bei r gleich 0 verschwindet. Und das heißt, du hättest im Zentrum deines Potentials keine Kraft. Das heißt, damit hättest du den Gradienten von r im Zentrum auf. Ja, stimmt jetzt nicht ganz, was ich sage, aber das ist die Idee dahinter. Ne? Das heißt, du setzt erstmal eine Randbedingung an den Gradienten von Phi fest. Und jetzt musst du es ja nochmal integrieren. Ne? Also, das heißt, du kriegst dann Phi ist sowas hier. So, und jetzt könntest du das Potential zum Beispiel im Unendlichen auf 0 legen und dann bekommst du so ein Integral hier.
Okay.
Aber gut, das ist jetzt für den kugelsymmetrischen Fall. Ja, schon mal interessant. Aber zeigt dir das Hauptproblem. Du musst irgendwo Randbedingungen festlegen, und zwar 2 Stück. Und das macht man normalerweise so, indem man sagt, okay, ich will bei irgendeinem Radius das Potential auf 0 setzen. Kann ich ja machen. Indem ich hier zum Beispiel auch einen anderen Radius einführen könnte. Und ich will, dass das Potential im Zentrum einen flachen Gradienten hat. Kannst du auch anders machen. Du kannst hier zum Beispiel anfangen und dann sagen, okay, ich integriere einmal. Nämlich so, unbestimmt. Und brauche dann hier eine erste Konstante. Und dann machst du es nochmal. Hast du also dann das hier. Dann bekommst du das hier noch dazu. Siehst du, das wird giftig, ne? Und bekommst noch eine zweite. Ne? Und dann kannst du beide Konstanten so wählen, dass das Potential die Eigenschaften kriegt, die du gerne hättest. Ne? Wenn es im Zentrum nicht divergieren soll, dann setzt besser C1 gleich 0. Und dann kannst du ja mal eine Quelle annehmen, wie auch immer du willst. Ne? Also eine Delta-Funktion oder ein Potenzgesetz oder irgendwas. Ne? Und dann kannst du die gleich wieder lösen hier. Und die zwei Konstanten liefern dir den Randbedingungen.
Danke.
Keine Ursache. In 3 Dimensionen geht es auch, oder?
Ich will kurz mein Handy fotografieren, das gleich ab.
Wenn das Ganze Fourier transformierst, ne? Dann steht hier minus k Quadrat gleich gut Tilde. Und dann kriegst du Phi ist einfach das hier Fourier zurücktransformiert. Ne?
Sind die Randbedingungen dann beide in dem einen Integral, oder?
Das sind aber überhaupt keine Randbedingungen. Da musst du jetzt eben, also so geht es auch, ne? Du kriegst da eine Lösung und dann musst du große Mühe geben in Randbedingungen.
Okay.
Next.
Ich hatte ja in dem Bereich auch in der Bachelorarbeit, haben Sie noch geprüft gehabt, so ein bisschen gehabt. Und wir haben ja jetzt wirklich die ganzen, es war ja grundsätzlich noch linear, alles für die Strukturen und so. Und wir haben ja dann die
Vorsicht.
Oder was?
Wir haben Funktionen so gewählt, dass lineares Wachstum identisch reproduziert wird. Die Trajektorien, die wir rauskriegen, gelten nicht linear.
Stimmt. Ja. Okay. Jetzt was. Aber weil ich hatte ja zu eben dann den Vektormoden, die eben noch dann existieren, also
Okay, ja.
zu der Volatilität und den Velocity Dispersion Tensormoden.
Ja.
Aber das heißt, man kann schon relativ lang annehmen, dass es alles erstmal keine wachsenden Moden drin hat.
Ja, auf dem zweiten Übungsblatt haben Sie ja gesehen, wenn Sie mit einer Rotationsmode anfangen, dann stirbt die aus und die fällt wie 1 durch a Quadrat ab. Das heißt, selbst wenn Sie am Anfang eine hätten, nach ganz kurzer Zeit haben Sie sie nicht mehr. Immerhin, seitdem der CMB freigesetzt, also der Mikrowellenhintergrund freigesetzt wurde, ist die Rotationsmode auf ein Millionstel abgefallen.
Ja.
Spielt keine Rolle mehr.
Ja.
Sie bauen eine neue auf, ne?
Ja.
Durch nichtlineare Entwicklung.
Genau.
Das schon, aber die Primordiale ist weg.
Die
Ja. Okay.
Alles klar, danke.
Ja, hallo. Ich bin eigentlich gerade auf der Suche nach einer Masterarbeit und ich wollte mal fragen, ob Sie noch Platz haben. Ich weiß, dass Sie immer sehr viele Studenten in der Gruppe haben.
Das hängt davon ab, wann Sie anfangen möchten.
Also, wenn es möglich wäre, würde ich bis Ende nächstes Jahr fertig machen. Also,
Das heißt, Sie würden so im Januar anfangen ungefähr.
ja, also wenn es noch möglich wäre, würde ich gerne vor dem Weihnachten schon ein bisschen lesen, sowas.
Es wird knapp, aber es geht.
Ja,
Also kommen Sie doch mal in meine Sprechstunde.
okay.
Dann können wir uns über mögliche Themen unterhalten und genauer darüber reden, wie Sie den zeitlichen Ablauf vorstellen und so,
Okay.
wann Sie anfangen möchten und so weiter.
Also mit dieser Zeit haben Sie dann einen Platz.
Es wird am Anfang knapp.
Okay. Und
Aber-
Januar und Februar, das wäre das oder?
Februar wäre besser, aber gut, Januar geht auch, ja.
Okay. Ja, aber das ist schon eine gute Nachricht für mich.
Kommen Sie mal vorbei, dann reden wir
Okay.
mögliche Themen
Okay.
und schauen mal, ob Ihnen das wirklich gefällt. Ne?
Okay. Ja, das finde ich gut. Ja. Wann haben Sie dann eine Sprechstunde?
Dienstags von 4 bis 5,
4 bis 5.
16 bis
Ja,
17
ja.
Uhr. Ne? Büro Nummer 209 im Philosophenweg 16. Eins höher, genau.
Ja.
Da oben.
Okay. Büro nochmal?
209.
Okay, alles klar. Danke.
Ganz hinten rechts.